Hi, okay. For this video, I'm going to talk to you a little bit about interpretations in FOL. So I told you earlier that, so unlike TFL, where we had one tool that we could use to test either validity or invalidity. So with a truth table, you can show that a valid argument is valid. With a truth table, you can show that an invalid argument is invalid. In FOL, we need two separate tools for those two different tasks. So to show a valid argument is valid, we use natural deduction. And in a later video, I'll give you the extra rules for natural deduction for FOL. And to show that an invalid argument is invalid, we use interpretation. So that's the thing we're going to practice here today. Okay, what's the idea behind what an invalid argument does? Well, it's kind of like what a row of a truth table does in TFL. What do I mean by that? Well, think back to the truth table test for invalidity. If you want to show an argument's not valid, what you need to do is the truth table for all the premises and the conclusion at once, and see if you can find a row of the truth table where all the premises are true and the conclusion is false, right? So say we have an argument like this one. Here's an invalid argument. If A, then B, that's premise 1. Premise 2, B, therefore conclusion A. That's an invalid argument. Suppose I wanted to show that. Well, I'm going to set up a truth table for all three of those sentences. A arrow B, B, and A. If I'm doing a truth table for all of those things together, well, my first step is I collect up over at the left here all the atomic sentences that appear in any of those premises or the conclusion. In this case, there's just two, A and B. And then the first thing we do setting up the truth table is I set out all the different rows I'm going to need, showing all the different combinations of truth values that A and B could have. So we could have both true, we could have A true and B false, we could have the other way around, or we could have both false. And that's it. There's no other possible combination of truth values, right? It's just those four. Those are the only four possibilities. So here's what's happening on each row of the truth table. I'm saying, suppose the world is like this. Suppose I'm telling this story where A and B are both true. Well, then I apply my truth table rules to figure out, is this sentence going to be true in that situation? How about this one? How about this one? Now remember again the definition of validity. Validity says it's impossible to have the premises true and the conclusion false. Impossible. So there's no way, there's no possible story you could tell where the premises are true and the conclusion false. That's a valid argument. So if I want to say an argument's not valid, then I want to find a row of the truth table that is a story, a way things could be, where the opposite is true. If I want to show it's possible to have this true and this true while this is false, I want to find which of these four possibilities is that one. So let's see, if I'm looking for a possibility where B is true, A is false, but A arrow B is true, well, that looks like it might be this one. So if I wanted to show that this argument, this, therefore this, is invalid, I just point here and say, well, here's a way things could be. If A is false, B is true, then you've got true premises and a false conclusion. Okay. The reason why truth tables don't work for us anymore in FOL for showing that something's valid is you're not generally going to have finitely many ways the world could be. So as far as TFL is concerned, the only thing that matters is whether A is true or B is true, or both or neither, when we're looking at this argument. So as far as TFL is concerned, there are only four possible stories. There's only four possible ways the world could be. This one, this one, this one, this one. If I had three atomic sentences, then there would be 8 possibilities. But that's more, but it's still only finitely many. So if I want to show that something is impossible, namely true premises and false conclusion, I just have to go through those 4 or 8 or 16 or however many possibilities and check all of them. But we can't do that in FOL. We can, though, do something like pointing to a specific story. So interpretations in FOL are like specific stories about how the world could be. And just like with truth tables, there's a certain part of the story that's up to you, right? When you're telling a TFL story, you get to decide, for each of the atomic sentences, are they true or false? You can just decide which row of the truth table you're going to look at. But with a complex sentence that has a connective in it, there are rules that say, depending on whether this is true or false, depending on whether this is true or false, the sentence as a whole is going to be true or false. You don't get to decide directly whether A arrow B is true. You only get to decide whether A is true, whether B is true. We're going to have something similar in FOL. So I'm going to illustrate this by means of an example. I've put up in the video here an example of an argument that we encountered back at the beginning of the class before we'd actually started learning FOL, before you were in a position to symbolize those sentences. And we had an argument, we had a debate in class about whether this argument is valid, and I tried to persuade you that it was by doing something that secretly was actually doing interpretations on the board. So hopefully some of what we do, some of what I do in this video will look familiar, because we did it before. Okay, first step before I start doing an interpretation, let's symbolize that argument. So right now it's in English, let's put it into FOL. So premise 1, everybody loves Mary. So that looks to me like a universally quantified sentence. That everybody, that sounds like a special logical word that makes me think universal quantifier. What else do we have? We have something that looks like a name, Mary, that looks like a name. So I'm going to start filling out my symbolization key. I'm going to say the name M. That stands for Mary. What are we saying about Mary? We're saying, so what's left, the only word we've got left is loves. Loves, that sounds like a predicate word. I think loves, the usual sentence about loving, that's going to take two names. George loves Mary, Mary loves George. It's got two spaces for name, so I think we want a two-space predicate here. So I'm going to use L, that'll be my predicate letter for loves. I think this is a two-place predicate, so I'm going to put two variables after there, and I'm going to say, here's what goes in my symbolization key. X loves Y. That's what LXY says. I haven't done a video on this yet, but you will have noticed from your textbook that when you're doing symbolization keys in FOL, as well as names and predicates, you need a domain. So I need to say who I'm talking about. I think I'm going to be fine if my domain is people. When we have a quantifier marker word like everybody, that sounds like we're saying all people love Mary. So I'll say that's my domain. Domain, people. Okay. So if I want to say everybody loves Mary, I think, so we're talking about, let's see, here are two possibilities we might get from here. So as far as we've figured out, we're doing something that involves a universal quantifier. It involves this two-place predicate LXY. It involves Mary. There are two ways I could combine those things. I can say for all X, X loves Mary, or I could say for all X, Mary loves X. Take a second and convince yourself of which of these is right. Maybe you paused it and maybe you paused the video and thought about that. I'm going to erase the one that I think is wrong. So our original sentence was, everybody loves Mary. I think this second one says, Mary loves everyone. That's not what we want. We want this. So that's premise 1. Premise 2, actually let me come back to premise 2 because the conclusion is easier. So we're going to have premise 1, premise 2, therefore conclusion. So our conclusion is Mary is a firefighter. So Mary, we've got that name already here. If I pull Mary out of that sentence and leave a blank, I wind up with blank is a firefighter. That sounds like a predicate. It's not on my list yet. The only predicate I have so far is loves. But now, okay, blank is a firefighter. That's got one blank in it, so we have a one-place predicate. Let's call it F. FX stands for X is a firefighter. Okay, our conclusion is that Mary is a firefighter. That sentence just looks like this. FM. I take this thing with one gap, X, and I plug the name M, Mary, into it. We get FM. That says Mary is a firefighter. Okay, next. Mary loves only firefighters. I've told you before a lot of sentences that you want to symbolize in FOL, we can, if you think about rephrasing the English into something that says the same thing, you'll be able to turn it into either all F's are G's or some F is a G. And I gave you formulas for instantly replacing these things with FOL. So all F's are G's. That looks like for all X, Fx, arrow, Gx. Some F is G, that's there exists an X such that it's an Fx, such that X is an F and X is a G. I think we can rephrase that premise 2, that one. Mary loves only firefighters. I think we can rephrase that in the form all F's are G's. I'll give you 2 ways we might write this. This is kind of a first step to turning it into that form. Mary loves every firefighter. Do you think that says the same thing as premise 2? Here's a different one. Everyone Mary loves is a firefighter. Okay, so this first question I'm asking you is, look at sentence A, look at sentence B. Sentence A, Mary loves every firefighter. Sentence B, everyone Mary loves is a firefighter. I want you to think to yourself, looking at sentence 2 up there, I gotta point that way. Sentence 2, Mary loves only firefighters. Do you think that says the same thing as sentence A? Do you think it says the same thing as sentence B? Try to convince yourself. I think it means the same thing as one of these. You got an answer? Okay, I'm going to erase the one that I think is different. I think that sentence we started with, Mary loves only firefighters. It doesn't tell us that she loves all firefighters. Maybe some of them are jerks. But it does tell us, well, it says she doesn't love anyone who isn't a firefighter. So everyone she does love is a firefighter. That's what I think it says. Did I write that too small to see in the video? I guess we'll find out. Everyone Mary loves is a firefighter. All people Mary loves are firefighters. That's the pattern we're going to use. So if I want to say everyone Mary loves is a firefighter, then I'm going to write something like this. It's going to be for all X, something, arrow, something. All, what am I putting here? People Mary loves. So for all X, if Mary loves X, then X is a firefighter. Okay. This is how we can go from Mary loves only firefighters into something of this form. Now we just have to figure out how to turn Mary loves X into something in FOL, turn X as a firefighter into something in FOL. So Mary loves X, I write that by saying LMX. Mary loves X. Maybe some of you are confused. I said in my symbolization key, the second blank, the second variable spot was Y. Now I'm calling it X. Remember, which letter you use, which variable you use, doesn't actually mean anything except in the pattern of repetitions within a sentence. So what's going on here in this entry in the symbolization key, there's this pattern between that X and this X, that Y and that Y. All that the difference between X and Y is telling me is, so when I'm looking at what this formula in FOL says, I look at this partial sentence, this gappy thing in English, and I say, well, the blank at the beginning, the person who's doing the loving, that's the one that goes in the first variable spot. The person who is loved here goes in the second spot. Okay. So over here, the fact that I'm using X, what matters there is that that matches the X here in the quantifier, and it's going to match an X after the arrow. If I used Y here and after the arrow, I would say exactly the same thing. Okay, so in the second part I want to say X is a firefighter. That's just fx. Okay, so the important thing here is that this quantifier says no matter what you put in the gap I'm calling X in the thing that follows me, you'll get something true. So no matter what you put here and here, you get something true. If I replace that X with a Y, well, since we have the same pattern of repetitions, the Y is here, here, and here, I say the same thing. I'm saying no matter what you put in the gap I'm now going to call Y, that's those gaps, you'll get something true. That's exactly the same as what I said before. Okay. So this is my premise 2. For all X, I'm going to go back to X. L, M, X, arrow, F, X. That's our argument symbolized. Now, let's try coming up with an interpretation where the premises are true and the conclusion is false. That's the thing we're going to try and do. We're going to fail, because this is a valid argument. But I'm hoping that you'll remember the sort of steps that we went through previously. Okay. So, here's what's going on. I want to tell a story. I'm going to try to show that it's possible to have true premises and false conclusion. If I were in TFL, telling a story would just mean telling you about each atomic sentence, is it true or false? In FOL, because we have subatomic structure, instead what I do is I tell you about the things that show up in my symbolization key. Just like in TFL, the things that show up in your symbolization key are atomic sentences. So, in an interpretation, I'm going to have to tell you about the 3 kinds of things that appear in an FOL interpretation. A domain, names, and predicates. Sometimes you won't have any names, but you'll always have a domain and predicates. Okay, here's what happens when I tell a story. Here are the parts that are up to me, the parts that I get to decide. It's those 3. When I'm picking a domain, what I do is I give you some number of objects. I give you a bunch of objects. Now, I should say there are multiple different ways of doing interpretations. There are multiple different ways of filling in these 3 bits of information. I'm going to give you just one. Most years I would show you a few different things and say pick whichever one is easier. But we have fewer lectures than usual because of the strike. So I'm just going to give you one way. I'm going to give you what I think is the best one for the kinds of questions that'll be on the exam. I'm just going to teach you how to give an interpretation by means of a diagram. So if I want to say, here's the domain in my interpretation, I just draw in my diagram. I'm going to use this area to draw my interpretation. I draw some number of points or dots, or if you like, little stick figure people. Let's say there are 4 people. It seems like a reasonable number. So here's a person, here's a person, here's a person, here's a person. Okay, there's my domain. I have answered question 1. Who's in the domain? Those 4 people. I don't know anything about them, but I know there are 4 of them. I'm about to tell you information about them by means of names and predicates. Okay, names, however many names I have. In this case, I only have 1 in the sentences I'm doing an interpretation for. What I have to do for each name is put that name on a person. I have to say which of those people in the domain is Mary. Now, remember, it's possible for one person to have more than one name, but it's not possible for one name to go on more than one person. Each name has to go on exactly one person. So let's say this one. I've just decided. Why is this one Mary? Just because that was my choice. I could have put Mary somewhere else. We'd wind up with a different interpretation. That's okay. Why do we have 4 people instead of some other number? Because I chose to put 4. That part is up to me. Okay, I've done those 2 things. Now, predicates. What do I do for predicates? Basically what I need to do is say, so take any given predicate, which will have some number of gaps, 1 or more. I need my interpretation to tell you. So if we had an atomic sentence that just applied the predicate in question to whatever combination you like of people from the domain, I need to know whether it's going to be true or false. Let's start with this one place predicate. Blank is a firefighter. So I need to know, no matter who I fill in this blank with, I need to know of that person. Maybe just so we can tell them apart, I'll call these people 1, 2, 3, and 4. So I need to know, is number 1 a firefighter? Or rather, if I put a name of number 1 in the X blank, is X is a firefighter going to be true or false? I need to know, is number 2 a firefighter? Is number 3 a fighter? Is number 4 a firefighter? Here's how we show that in a diagram. I'm just going to circle the people who are firefighters. So I'm going to say, how about this? I'll put an F to label. I'm saying everybody inside this circle is a firefighter, everybody outside it is not a firefighter. You can think of this sort of circling thing as being like Venn diagrams. If I had multiple one-place predicates, you might think of, so something like this. If these are the F's and these are the G's, then any person in here is an F but not a G. Any person in here is both an F and a G. G but not F. Outside, they're neither. That's the kind of thing that we do for one-place predicates. Okay, you just draw circles. Two-place predicates are more complicated. So when I've got two gaps, so L blank blank, I need to know for every combination of people, or every permutation of people, whatever. Anybody I could put in here and anybody I could put in here, I need to know if it's true. So I need to know, does 1 love 2? Does 1 love 3? Does 1 love 4? Does 1 love 1? Does 2 love 1? Does 2 love 2? Does 2 love 3? Does 2 love 4? So I have to know for each ordered pair, do they love each other in each direction? Here's how we show that with a diagram. Arrows. Let's suppose Mary loves number 3 and Mary loves number 4. Maybe number 4 loves number 3. I don't know, what else do you want? Let's put more love in the world. 4 loves 2. 2 loves Mary. How about that? Here's what I've done. Pardon me. Wherever there's an arrow, that means the person at the tail of the arrow loves the person at the arrowhead. Wherever there's no arrow, there's no love. So 4 loves 3, we know because there's an arrow from 4 to 3, but 3 doesn't love 4 back because there's no arrow going back. In our diagram, nobody loves themselves. I didn't make anybody love themselves. Maybe let's fix that. Let's do that. Mary loves herself. You've got an arrow from her to herself. That's how you do it. Okay, that's it. We have completed our interpretation. We have filled in all the things that are up to us. Now, the other important thing you need about interpretations, aside from how to make your own, what you're allowed to tell in your story, what's up to you, we need to know about how to check whether each of these sentences that has more logical structure, whether each of those is true or false. Okay, I've made Mary not a firefighter. That part was up to me. This is just an atomic sentence. This sentence says, Mary is a firefighter. Well, I decided that 3 and 4 are the only firefighters, and I decided that Mary is person number 1. She's outside the firefighter circle, so this sentence is false. That's what I wanted. Remember, I wanted to get a sentence where we get true premises, false conclusion. What about this one? So sentence 1 says, for all x, L, x, m. That means it's saying, so look at this sentence. I'm taking the quantifier off and looking at the gap. That sentence says, no matter who you put in this blank, no matter which of the 4 people you put in there, we get a true sentence. So that sentence says, number 1 loves Mary, number 2 loves Mary, number 3 loves Mary, number 4 loves Mary. I have to check each of those arrows. And this sentence, because of the universal quantifier, is going to be true just in case all 4 of those arrows are there. So let's go check. Does number 1 love Mary? Yes, she loves herself. Does number 2 love Mary? Yes. Does number 3 love Mary? No, there's no arrow pointing that way. Does number 4 love Mary? No, there's no arrow pointing that way. So that sentence is false. I would have needed all 4 of those arrows to be there in order for this to be true. Okay, since we wanted to have an interpretation where we get true, true, false, we might think, okay, I'll go back and change it. I'll put more arrows in. We'll check on it that way. We'll do that in a second. I want to go through sentence 2 first, just to show you how this works. So sentence 2, same kind of thing. So we've got the main logical operator here is a universal quantifier again. So that means this thing says, look at the thing in the brackets. So we have L, M, blank, arrow, F, blank. This sentence, sentence 2, says, no matter what I put in the blank, as long as I put the same person there, I'll get a true sentence. So as long as it's the same person here and here, I get a true sentence. So I have 4 of them to check for 1, 2, 3, and 4. So now I'm looking at an arrow sentence though, right? So what I'm going to do is go through each of those 4 possibilities, each of those 4 people, and check, is LM1 true? Is LM2 true? Is LM3 true? Is LM4 true? Is F1, F2, F3, F4, are those true? And then I'm going to do the truth table for arrow on those 2 things. So if I'm looking at number 1, does 1 love 1? Or sorry, does Mary love number 1? Yes, she does. Is number 1 a firefighter? No. So for 1, I get true, arrow, false. That is false. What about 2? Does Mary love 2? No, she doesn't. So LM2 is false. Is 2 a firefighter? No. So I have false, arrow, false. From the truth table, that's... Pausing while you remember. False, arrow, false is true. Remember, the only way to make an arrow sentence go false is if you have true antecedent, false consequent. Okay, number 3. Does Mary love 3? Yes. True. Is number 3 a firefighter? Yes. True. So we have true, arrow, true, which is true. Number 4, same again. Mary does love 4, so that's true. 4 is a firefighter, that's true. True, arrow, true is true. Okay, so we've checked all 4 cases. Now remember, we were checking them because of a universal quantifier. That means we needed to make sure all 4 of them were true. But they weren't. Number 1 was false. That means this sentence is false. Okay, so let's just back up a second. What this means is we gave a story here. I told you a story about how many people there are, the domain, which of those people is Mary, who's a firefighter, and who loves whom. In the story as I told it by means of my arrows and circles, I should apologize, by the way. This would look much better if I had multiple colors, but all my colored markers ran out of ink. I went and bought a box of new markers right before everybody was staying home, but it turns out they're all black, so this is what we have. Okay. I told that story, and then I went and checked. In my story, does everyone love Mary? That turned out not to be true. Does Mary love only firefighters? Again, that turned out not to be true. Is Mary a firefighter? That's not true, which is good. That's what I wanted. So now I'm going to go back and try and change my story, because these parts were up to me. So let's see. I want to make sure everybody loves Mary. I can fix that just by adding in more arrows. So let's see. Who doesn't love Mary? Mary loves Mary. That's good. Number 2 loves Mary. That's good. Number 3 doesn't love Mary. So let's put another arrow in. I'm going to make that a double arrow. 1 and 3, they love each other. Number 4 also doesn't love Mary. Again, let's make this into a double arrow. Mary loves 4, 4 loves Mary. Okay, so now if I check this thing, I'm checking, does 1 love Mary, does 2 love Mary, does 3 love Mary, does 4 love Mary? All 4 of them do. So now this is true in this interpretation as I've modified it. I can check the conclusion again. Is Mary a firefighter? No, she's still outside the firefighter circle. So she's not a firefighter. That's good. Now let's check premise 2. Premise 2. Mary loves only firefighters, or in other words, everyone Mary loves is a firefighter. So I check number 1. Does Mary love number 1? Yes, because that is Mary. Is number 1 a firefighter? No, still not a firefighter. Ooh, that's a problem. So this sentence is going to be false, no matter what's going on with the other people, right? Because this universally quantified sentence says, no matter who you put in here, into that X gap, you'll get a true sentence. I found somebody who makes it false, so I don't have to check the rest of them. Okay. Mary does love Mary, but Mary is not a firefighter, so the arrow sentence is true, arrow, false. Bad times. So if I'm going to modify this interpretation to give me the pattern I want, true, true, false, I'm going to have to change it so that either Mary doesn't love herself anymore, or so that Mary is a firefighter. But maybe you've already figured out I'm not going to be able to do that. I'm not going to be able to do that without making either premise 1 false, right? If Mary doesn't love herself, then there's somebody who doesn't love Mary, or making the conclusion true. If Mary does love herself, but she's a firefighter, then the conclusion is going to be true, not false. Okay, so this project is going to fail. But that's the kind of thing that we're trying to do. Okay, when you want to show that an argument's invalid, you want to give an interpretation where you get true, true, false. The things that are up to you are 1, 2, 3, these kinds of information. How big is the domain? What's the domain? Which member of the domain does each name pick out? And which parts of the domain make each predicate true, which parts of the domain make each predicate false, depending on how you fill in the gaps in your predicates with members of the domain. And then what's not up to you, what follows from the choices you make about 1, 2, and 3, those bits of information, what follows from them is whether sentences that aren't atomic, sentences that have logical quantifiers or connectives in them, whether those sentences come out true or false. So you get to answer this information however you like, and then the logic gives you rules for figuring out whether these complex sentences are true or false. That's interpretations. The end.